Hi, welcome to the lesson 19D, Solids of Revolution. The goal of today's lesson is to calculate the volumes of revolutions of functions. When we began looking at integrating and finding the areas under curves, we looked at functions and we divided the area under the curve, between the curve and the x-axis, into rectangular strips of lower rectangles, as we can see here, and upper rectangles, as we can see here. And to find the approximation of the area under the curve, we multiplied, when area is length times width for a rectangle, we multiplied the width by the sum of all the lengths, or the heights of each of those rectangles, from I equals 0 to n minus 1. This is for the lower rectangles of the function evaluated at x sub I. And then for the upper rectangles, we looked at the width multiplied by I equals 1, in this case, up to n of the same function x sub I. So this is length times width and the sum of all those rectangles, and we realized that the limit as n approached infinity, as we increase the number of those rectangular strips, we narrowed down the width of each of those, and so the limit as n approached infinity for the sum of all those rectangular strips for the lower rectangles, that ended up being equal to the actual area, which was equal to the limit of the upper rectangles, the area of the upper rectangles. So by narrowing all those widths of all these rectangular strips into smaller and smaller and infinitesimally small widths of each of those rectangles, we ended up getting a very, very good approximation for the area of under the curve. So it turned out that even though the area of the lower rectangles was supposed to be smaller than the upper rectangles, the sum of all the upper rectangles, when n approached infinity, it ended up that those two were equal, and the actual area was between those. Therefore, the lower rectangles equal the actual area, which equaled the upper rectangles. So now we're going to extend this a little bit, and we're going to start by, continue, I guess, this process by taking these and imagining that we're going to start rotating this function about the x-axis. So it's actually going to end up forming, if you can visualize this, each of these rectangular strips is going to rotate around, and it's going to form discs, kind of like coins, around the x-axis, and in a form that will approximate the curve in both cases. So we're going to get these rectangular discs. Now if these discs are fairly wide, then the discs are actually going to approximate the shape of cylinders. And we know that the volume of a cylinder, the cylinder is just a fancy prism, where we take the area of the base multiplied by the height, and the base in this case is the circle. So the area of the base is pi r squared multiplied by the height will give you the volume of the cylinder. So then we want to actually decrease the size of the height of the cylinder. We want to make it much, much smaller, just like we narrow down the widths of all those strips previously. We want to narrow down the height of these cylinders so that they actually end up becoming discs, and the discs will look something like this. And so we end up actually getting a volume. We can get a volume of rotation, and the volume ends up being the limit as h approaches 0 of the sum of x equals a, which is this the lower limit, that's the x value here, up to x equals b. And because we know that the formula for the volume is pi r squared h, we're going to have pi here. And the function is actually f of x squared, because it's pi r squared, and r is the function, multiplied by h. Well, as h approaches 0, we can then extend this idea to integrals and say that it's going to be then the integral from a to b of pi f of x squared dx, because h is becoming closer and closer to 0. And then because pi is a constant, we can kick that up front, so the volume is pi evaluated from a to b of y squared dx. Okay, so this now is the formula that we can use to calculate the volume of rotation. So we just take the function, we square it, we take the integral of that, and then we multiply the result by pi, and that gives us the volume of rotation. So that's basically the long and the short of the foundation of integrals of the volumes of rotation. So what I'd like you to do before class tomorrow is take a look at examples, the examples in the textbook on page 490, 492, and 493. And then take a quick glance at the practice questions, which I'm going to assign you. And just sit back and relax and enjoy our examples in class tomorrow. And after we finish those examples, you're going to have some time to work on the practice questions, and then you will be experts in finding the volumes of revolution. So thanks for watching, and we'll see you in class.